slide presentation. We've got Calculus AB, and actually this will be applicable to students who are in BC as well, because a lot of this material they're going to see on their AP exam. And we're going to be looking at some of the free response questions from the 2018 exam. And I think I'm going to start with one that I think will be most useful for everybody, but I'm happy to take requests as well. There are 6 problems, so I don't think we're going to get through all 6 of them in completion, but we'll do the best we can to help you guys out. So the first 2 problems are calculator friendly. We've got an escalator problem where people are getting on and off of an escalator. Problem 2 is also a calculator friendly problem where we've got a particle moving and we're looking at its movement and velocity, acceleration, etc. And then 3 through 6 are all no calculator problems. And we're looking at graphs of a G and an F function and how they relate to each other. We've got a problem about a tree growing. And of course, we have a table given to us. That's a pretty common type of free response problem. Another movement problem. And finally, we have a differential equation and slope fields problem. So so I'm going to share with you my doc cam here, and we'll go through some of these problems one by one. And I think that I'd like to start, like I said, with problem number 6, which is, I feel like a lot of students learn this material about slope fields and differential equations. They learn it briefly, and then they find that they get really intimidated by the slope fields or finding a particular solution. Okay, so we'll start with this problem number 6. And if there's a problem type that people want to look at, please do let me know, and I'm happy to go over that with you. So problem 6 says, consider the differential equation dy dx equals 1/3 x times y minus 2 quantity squared. For those of you that are with me here, can you give me a message in the chat board here? Do these problems intimidate you? Is this something you do want to learn about? Can we tackle the position one next? Yeah, that sounds good. Okay, so let's get through the differential equation, and then we can look at the position problem, because those are definitely pretty likely to show up on the AP exam as well. Alrighty, so what I think is the cool thing about differential equations and slope fields is they seem intimidating, but they really incorporate a lot of pretty simple steps and simple processes that I think you'll be able to handle pretty well. So the first thing is this slope field has been graphed, and you probably know this, but just as a kind of a quick review, the slope field is graphed point by point based on what this equation is right here. So for instance, at the point 1, 0, if you put in 1 for x and 0 for 2, what does that give us? 1/3 times 1. And then we're putting 0 for 2, so we got -2 squared is 4. That gives us 4/3, a little bit more than 1. And what we would see here is a little slope, little dash. Yay, you see it now? Oh, I'm so happy. Hooray, hooray. Can you see my face too? Me making silly faces? Okay. Anyway, hooray. Thank you guys. Thanks for bearing with me. This is my first time using the Crowdcast program. So I love presenting on video, but this is the first time I've used this program. All right. Okay. So somebody had a question back there about actual mathematical question. If you were to get a slope field, how do you think we would be expected to answer it on another sheet of paper? Like when we take a picture, do we need to draw a new slope field on paper? Well, on this particular problem, from the 2018 exam, you were not expected to actually create the slope field. Usually on slope field type problems where they actually want you to create the slope field, they will give you a graph. I'm just going to slide this to the side for just a second. They would give you a set of axes, and they would give you very specific points, maybe 12 points, 0, 0, and 1, 0, and 2, 0, 0, 1, 1, 1, 2, 1. Maybe, for instance, these 9 points, and they're usually, I don't think I've ever seen it where they weren't just whole number grid mark points. And you would go through point by point and plug in the values and estimate the slope field. So to give you like a very simple one, like dy dx equals, and maybe the value is 2x minus y. And so I'm not going to do this whole thing here, but you would go through point by point, and you'd say, maybe for instance, for the point here again at 1, 0, you'd say, okay, plug in 1 for x and 0 for y. So I'd get 2 times 1 minus 0. Okay, I get 2. So what I would do then is graph in a dashed line that looks like it has a slope of 2. So a slope of 1 would be a perfect 45-degree angle. So I'd make it just a little bit steeper than that to get a slope of 2. And then maybe here for this point here at 2, 0, that'd be 2 times 2 is 4 minus 0. So I'd want an even steeper slope. And it's sort of, you just artistically, the best you can, estimate visually each of those slopes. Here at 0, 0, 2 times 0 minus 0. So we have a slope of 0. And so you'd have a perfectly flat line like that. And if you happen to come up, you wouldn't get this here, but if you happen to have a problem where it was a ratio and perhaps it was divided by 0, maybe x over y, and the point you were using was 2, 0. So that would be 2 over 0. So you would do a dash like that, which was straight up and down for an undefined. Yes, when you see, the question is, for this year's exam, we can draw a slope field on our paper like you did, and then submit a picture of that. To get into the nitty-gritty details of the logistics of this year's test, if you have a printer, which would be lovely if we all had printers, you would print it off and this grid would be on the paper. Otherwise, yes, I believe they would just ask you to recreate it like that. You would draw it out and then you'd submit a picture. If this was on the test for this year, ask Maria, since the question will be online and on the screen, if we choose to solve it on paper, do we have to redraw the graph and then draw the slope field? Again, for a problem like this one that I made up, I would think yes. For a problem like this one, good point. This would be a pretty tough one for you to recreate on your own. So I have to imagine that they would have a very simple, something very simple like that. Let's get into the solving of this for now, and we'll have to, as we get closer to the test, they'll be revealing more details about the logistics and how you're going to actually interact with your screen and be able to create your solutions that you can present to them. So this one says, hey, here's the slope field. It's already created for us of the given differential equation. And of course, the differential equation is just an equation that contains a derivative, and our dy dx is the derivative. It says sketch the solution curve that passes through the point 0, 2. So that's kind of one problem. And then separately, sketch the solution curve that passes through the point 1, 0. Those are two separate solutions altogether. They're just having you do them both on one graph. So here's what I think is so simple and straightforward about this type of a problem. And I'm hoping to take your anxiety level down about this, because I know when I first saw these, when I was your age, I had a lot of anxiety about them. So the solution curve through the point 0, 2. I'm going to look at the graph. Where's 0, 2? Okay, right here. They put a dot there for us, which is handy. And what you want to do is you're following the flow of the slope that's given to you there. And hopefully you see, okay, I have a slope of 0 there, and it just kind of keeps going, So what you're doing is you're following the trend of those slopes, and you're going to just draw in a line that goes straight through that. This is about as straightforward, no pun intended, straightforward as a solution curve can possibly get. Now, the one for 1, 0 is going to take a little bit more artistry from us. So here's 1, 0, and what you want to see is like, oh, there's sort of this, you can see it kind of goes up and over. So I'm going to trace through, and again, you're being as artistic as you can, following the curve as best you can without getting too crazy about it. So we follow it. And some people will have slightly different curves, but similar, and we could all have it done correctly. You do the best you can on these. And then I'm going to follow this, and I'm not sure exactly where it crosses through, but we're just going to do our best to follow the trend of the slope field. It kind of looks like it comes down like this. And then it looks like there's a symmetry to the other side and kind of flow up like that. So again, on these, you take the point that they provided and just follow the path of the slope field as best you can. Okay. Part B says, let me scroll this up just a little bit. Part B says, let y equals f of x be the particular solution, sorry, I'm wiggling this around, to the given differential equation with the initial condition f of 1 equals 0. So that goes with the sketch we just did that went through 1, 0, right? Because x is 0 here and the output value y is, x is 1 and the output value y is 0. So what we're going to do is, first off, the particular solution would be basically the, scroll down here, would be the integral or the solution of this dy dx equation. And we will get to that in part C. They actually asked us to do that in part C. For part B, what we're saying is we've just got this sketch of the particular solution. We don't know the equation of it yet. And we're going to use an equation for a line tangent to that graph at that point to do an estimate. This is an example of linear approximation. And again, this is something that's a pretty common, every year you're going to see some version of a linear approximation. So we'll do part B real quick now, and then part C is actually finding that particular solution. So let's start with part B, which is our linear approximation. I'm going to rewrite the dy dx so I can see it on the screen here. That's an x, quantity squared. Okay, I'm going to scroll up just a little bit here. And we know that f of 1 is 0. Okay, so anytime you see make an equation of a line, anytime you see linear approximation or line tangent to, I think the very first thing you want to think of is a generic equation for a line. Can anybody type in, I know it's a little hard to do this with a regular keyboard, but can you type in what generic equation for a line we should use? Anybody have ideas here? Okay, I see a couple good examples here. Oh, just a second. Holy moly. Okay, I see y equals mx plus b, which is an equation for a line. That's slope-intercept form. And then I see y minus y1 equals mx minus x1. They're both perfectly great generic line equations. I think the easiest one to use here, and the one I usually go to, is that slope point format, y minus y1 equals mx minus x1. So good job. Quite a few of you guys chose that one. And again, y equals mx plus b is not incorrect. I think just for me, this one is the easier one to use. It's called slope point. And the good news is x1, y1 is our point, and we already know our point. That's handy. I know that x is going to be 1 and y is going to be 0. So then all we have to find out is that m, that slope. So with the information we've been given in this problem, how are we going to find m? How are we going to find that slope? Okay, I see substitute. That might be part of it. I see derivative, plug in x. You guys all got it. Excellent. We are going to substitute our x and y values into dy dx. Beautiful. And of course, slope, derivative, interchangeable. So let's figure out what that is. And I'm going to just show you some fancy notation here. You've probably seen this, but dy dx, you put a bar, 1, 0. This means I'm going to evaluate dy dx at 1, 0. You don't have to write it that way, but just thought I'd share that with you. And so we're going to plug in 1/3. Let's see, x is 1, y is 0. And I actually just talked about this a few minutes ago when we were talking about the slope field. This is 1/3, and this ends up being -2 squared, which is 4. So that would be 4/3. Do you have to use that notation on the exam? I don't think that you have to use that notation. I'm just using it because I like you to, I like my students to be exposed to as many notations as possible so that when they pop up, when you see them in the future, they don't intimidate you too much. So you're like, I've seen that before. And it's just a fancy way of saying, hey, I'm about to plug in 1, 0. So what we figured out is our slope is 4/3. So we're writing our equation. So let's go ahead and throw those values in. Y minus 0 equals 4/3 x minus 1. And we want to use this to approximate f of 0.7. Folks, what the heck are we going to do here? How do we do that? Oh, excellent. You guys are on it. Let's see. Some people say plug in 0.7 as x. Yes. Does the slope coordinates, do they have to match the equation coordinates? Perla, I'm not sure I understand your question, except for that, yes, in order to get this slope, we had to plug in the original point. I'm not sure if that's what you were asking or not. So plug in 0.7, plug it in, change the equation to be f of x. Plug in the point. Yeah. So what we have here, and I'm going to get rid of the 0. I could, if this was an actual like value, I could add it to the other side, but I'm just going to write y equals 4/3 x minus 1. So what this here is my sort of my y equals. It's my equation that is the tangent line through. Bring this guy back here for a second. Sort of the tangent line that might be going through this point on the slope field, through that point on that particular solution. So now, do I need to call it y equals? Do I need to leave it as, or do I need to change it to f of x? Well, really, since the problem, sorry, I'm scrolling around here. Since the problem says let y equals f of x be the particular solution, and we have it in y equals form, but since y equals f of x, then we can also say f of x equals 4/3 x minus 1, right? Yeah. So now what we want to do is we're trying to figure out, excuse me, I misspoke. Y equals f of x is the particular solution, and what we did here is we used a linear approximation to approximate what the f of x is. So f of x equals, this is our, what you can say is f of x is approximately equal to this equation we came up with in the neighborhood of x equals 1. So this is only going to work really close to in and around that 1, 0 point that we had here. So this linear approximation, this linear, tangent line is not going to be a good approximation way over here, just right in that little neighborhood here. Do we have to say explicitly that f of x equals the equation? I don't think that you actually do, because that was already defined for you in the problem. What you do want to do, though, is say that you are approximating, and that's why we use the wavy equal sign like that. So we want to say f of 0.7 is approximately, and I've got 4/3. Now we're in fraction form, and I see a great suggestion from Daniela, which is change 0.7 to 7/10, because 0.7 and 7/10 are equivalent. So for plugging in for x, you could say 0.7 or 7/10. I'll go ahead with Daniela's suggestion, 7/10 minus 1. I'm going to actually, same thing as, I'll do it in decimal version as well. Not everybody would have thought of doing it in fraction form, right? And then we want to go ahead and simplify as best we can. So what am I seeing here? 7/10 minus 1, that's -3/10, right? And then likewise, over here, you would get -0.3. And this is where, when this is a non-calculator problem, you can see why what Daniela suggests is going to be a whole lot simpler if you want to reduce. The 3 is reduced, and you end up with 3 over 3 is 1. So I get -4/10, also known as -2/5. Now, here's a cool thing. Most of you on here have not taken, unless you're in BC and maybe you took the AB test last year. Here's a cool thing. On open response, especially on the non-calculator portion, you're allowed to leave values unsimplified. So technically, you could leave it like this. In my personal opinion, I feel better kind of taking it as far as I can when I know I haven't made any errors. But again, you are allowed to, and you'll see it in the rules. And even if you pull up, like for instance, the 2018, the instructions for this free response portion, it says you are allowed to leave the values in unsimplified form. You just want to make sure you've done all the mathematical, steps and the interpretation process accurately. So what we found is -2/5 is our approximation, and just kind of to tie everything back together to that graph. And Akshita, you also said -0.4, which of course -4/10 is another way of saying -0.4, 4/10 in decimal. So all of these are perfectly acceptable forms of the solution. And so we've got this, I've sort of made a mess of the graph here, but 1, 0 was our given point. We had this slope, and so is it somewhat reasonable that at point x equals 0.7, which is maybe about here, that our approximation might be at about -4.4? To scale, maybe not perfect, but it's within reason. It looks like a reasonable estimate there. Okay, now for kind of the tougher part of the problem, which is find the particular solution for this differential equation with the exact same initial condition. So basically what we're about to do is come up with the y equals for this curve here, the actual curve portion. Alrighty, Perla says your internet crashed, and you know what? If it does happen to you on the exam day, there is a makeup day, and let's all just hope that I've had so much video stuff on my computer's been crashing right and left too. So good juju on this. Good luck for May 12th for all of us. Okay, finding the particular solution. This is solving a separable differential equation. I'm going to rewrite once again our fun diffie-q. And I would love to know, take a poll of you guys out there, what's our next step? How do I start solving for a particular solution here? How do we get going here? Here's a hint, they're called separable differential equations. Okay, I see, I'm gonna read the question here. Okay, great. Getting great input from you guys. Thank you so much. Somebody asked, are you going to be able to see this video later? Yes, it'll be uploaded at another time later. I'm not sure if it's later today or tomorrow, but you will absolutely be able to kind of click back through and follow if you need to. There should be a link to all of the questions as well, so you can play with them. But back to this problem, yes, separate the x and the y. Z, I apologize. I'm not sure how to pronounce your name, but you got it. You separate the x and y. Ariana says combine the y's on one side and the x's on the others. You got it. So step number 1 is separate. Step number 2 is integrate. So here, because it's a x times this quantity y minus 2 squared, that's kind of what makes it separable, makes it easy to separate, because I can just divide the y minus 2 squared to the left-hand side of the equation. And in general, I think the smartest thing, the safest thing for you to do is to leave this 1/3 or any other constant. Leave it with the x stuff, because we're going to end up solving for y. So why move a 1/3 over to the other side and make things more complicated? So let's leave that 1/3 x over here, and we're going to multiply each side by dx. So we kind of did this manipulation where we divided each side by the y minus 2 quantity squared. We multiplied each side by the dx, and so we have now separated the differential equation. Ariana, great question. What part of the question lets us know we must separate the equation? Well, the only kinds of equations or differential equations we know how to solve when we are in Calc AB, the only type we know how to solve are separable. So because it was given to you and you were actually told to solve it, find this particular solution, it's implied that it is separable because that's the only way you're going to be able to do it. I gave an example earlier when I drew on here, this example, 2x minus y. This is a differential equation where you can graph it. We can go through and make a chart and kind of come up with each of the slopes and graph it, but it's not separable. There's no way to get the y with just the dy, and because of the minus sign. That's the problem here. I can't just divide. I'd have to subtract it over, but then how do I play around with it? There are no way to separate the x and the y there, even though it looks like there might be. So it's usually when things are multiplied together or divided by each other where you'll be able to separate them. Alrighty, so, but great question, because yeah, how do you know? Well, if they ask you to solve it, then it must be separable. Okay, so we've got this all here. So again, first step was separate. Second step is let's integrate. So I'm going to rewrite this guy as y minus 2 to the negative 2. And we're integrating. Take a moment. I'm going to give you some think time here. Take a moment, and if you would, go ahead and integrate both sides of the equation. And don't forget our friend plus c while you're at it. If one side seems harder than the other, that's okay. Just pick a side and get going. We're here to practice, so it's okay. All right. Rishika has a question about absolute values in integration. This particular problem does not have absolute values involved, so but there are some that do. So what I want to know is, oh, you meant in general, okay? Because we're talking about natural log type problems, ln problems. I'm going to try and remember to come back to that in just a second. I'm going to kind of focus on this problem, and then we'll talk about that. Yeah. So you're very welcome. Alrighty, so let's see. I have some people already typing in solutions. Looking wonderful, guys. Very good. Yeah, so because this is a -2 power, I need to use what I like to call reverse power rule. So we're integrating, and we're going to say, okay, I'm going to take this inner function y minus 2. I'm going to increase the power from -2 to -1, which then, of course, means we need to divide by that new power, which is -1. And then you want to look inside and go, ooh, I have this function inside here. Do I need to use reverse chain rule? Do I need to divide by the derivative of what's inside here? And luckily, if you look inside, the derivative of y minus 2 with respect to y is 1. So we don't have to worry about any chain rule going on here. Of course, this side would get a plus c. However, I'm going to write it for now. I'm going to write plus C1, and I'll kind of tell you my take on the plus C with separable differential equations in just a second. And of course, on the other side, it looks like everybody who typed it in got it correct, which is this is x to the first, so we're going to raise that x to the second. And of course, that was 1/3, of course. And now I need to divide by my new power, so I'm dividing by 2, and that's a plus c. I'm going to call it C2. So this is a constant. This is a constant. No, you don't have to show C1 and C2. I'm just kind of doing that to be obnoxious because if there's a constant here and a constant here, can't we just combine them together and make one constant, right, Akshita? So I'm just going to kind of clean this whole thing up. It's sort of a messy line I've got going on here. So I've got negative, and then this y minus 2 to the -1, which is the same thing as 1 over y minus 2. And then on the right-hand side, we've got 1/6 x squared. It could be x squared over 6 as well. It doesn't matter. And then I'm just going to write one big plus c here. I've combined these plus c's, and now this is just plus c. Okay. And so next, our job is to kind of figure out what's y equal to. And again, this is my deal with the plus c. I think this is kind of handy to keep in mind. So I have a negative here. I'm trying to get y by itself. So I'm going to just multiply through by a -1. So everything's getting multiplied through by a -1. So this is all now positive 1 over y minus 2. This is negative 1/6 x squared. Now, my take on this is if I multiply a constant by a negative, it's still just a constant. Sometimes you have to multiply by 2 or you divide it by 7 or whatever as you're solving. I like to just say it's still just plus the constant. You can have the negative follow, but this is like one place where I think you get a little freedom with the algebra, and you kind of just, I'm saying it's still just a constant. This constant's different than this constant. It's okay, still just a constant, because we're not solving quite yet. Okay, next step. Gosh, I need y equals, but I have 1 over. So you know what I'm going to do? I want the reciprocal of this. So does it make sense that we might take the reciprocal of both sides? So then I could have y minus 2, that's the reciprocal of this, and then I have the reciprocal of this whole thing, negative 1/6 x squared plus c. Now the plus c, since I took the reciprocal of this whole thing, the plus c does have to go in the denominator. Can we solve for the constant first? You could. I usually like to get a little further along to a y equals. I don't think that you're going to be wrong if you decided to do it on this line right here. I'm going to go ahead and do it on this line here, just cause. Is that smart? Probably not. I don't know. Because we're trying to solve for c. You're correct. Usually I try and get a little further along to a y equals, but then of course that means undoing what we've already done. So Danielle's question refers to the fact that we need to figure out, this is sort of, all of these versions here are sort of generic versions of the solution, generic solutions. And now we need to come up with that particular solution by plugging in our initial value, which was, of course, 1, 0. And again, you can do that on any of these lines along here. Daniela, I'll go ahead and use your suggestion. We'll go from this top line here. So if we're plugging in 1 for x, right? So that would mean we have 1 squared, so 1/6 plus c. And then on the left-hand side where the y's are, we're plugging in 0 for y. So I have negative 1 over, and then we have 0 minus 2, which is negative 1 over negative 2, or positive 1/2, right? Oops, that should be an equal sign right there. Pardon me. Plus c. And of course, c is going to be 1/2 minus 1/6. 1/2 minus 1/6. And of course, this is no calculator, so we're thinking, okay, 6. That means I've got 3/6 minus 1/6, which is the same thing as 2/6, or 1/3. So our c value is 1/3. Long story short, what we're trying to get to is a y equals. So I know that this value c, this c right here, actually this c right here, because I solved for this one, needs to be a 1/3, right? Positive 1/3. If I had solved from this version or this version, I would have gotten actually negative 1/3 for my c value. So it does matter. Wherever you stop and plug in, that's where you need your c value to go back into. So I stopped here, even though I was going to go a little further. So that's my 1/3. So long story short, I have this. Let's see. We had negative 1 over y minus 2 equals 1/6 x squared plus 1/3. Plus 1/3. We need to get y equals, because they asked us for this particular solution, so we need a y equals equation. So again, I'm going to distribute that negative through. That's why we simplify when we only have to, yeah. So I've got negative 1/6 x squared, so negative, this is now positive, negative, and minus 1/3. Again, let's do our reciprocal. So y minus 2 equals 1 over all of this. And of course, we can add the 2 over to the right-hand side. And there you go. We have our particular solution. Yes. Okay, so a couple of questions about the simplifying here. Again, I went from this generic solution over here. Okay, so I kind of backed up a few steps and I said, okay, I'm going to solve for c for right here. So this particular c is positive 1/3. So that's what I plugged in right here, positive 1/3 to the exact same equation. okay? And then I said, okay, I need to solve it for y. So first step, and I can show that in a different color here. First step that I did was I multiplied each side by a -1. I don't know if you can see that. It's a -1 and a -1. So negative times negative, I get positive 1 over y minus 2. And then here I get -1/6 x squared, and then I get a -1/3. So that's where the -1/3 came from. Okay, it was positive, now it's negative. Then I've got this equation here, and I can think of this is all over 1. So I took the reciprocal of this side, so it's y minus 2 over 1. Took the reciprocal of this side, so it's 1 over -1/6 x squared minus 1/3. And we're almost done. All I had to do was add this 2. So this fraction right here is that fraction right here, and then just plus 2. Excellent. Alrighty, so I want to take a vote, depending on who's out there still. I had a request for a movement. Okay, Zay, I'm going to go back to your question real quick. Excellent question. Sorry, before we move on. Zay's asking, but if I had waited to solve till down here, you are correct. If I had waited, instead of stopping up here, if I had waited to solve till I was down here, it actually all ends up working out just the way it should. Because if I plug in my 1 for x and my 0 for y, that's correct, right? 1, 0. So I get 0 minus 2 on that side. And I plug in my 1 for x. Okay, so I get -1/6, 1 squared plus c, right? So I have -2 equals -1/6 plus c. Uh-oh, I need to solve for c, so I'm going to take the reciprocal of each side. So I get -1/2 equals -1/6 plus c. And then when I solve, I get -1/2 plus 1/6 is c, which is -3/6 plus 1/6, which is -1/3. So when I take that -1/3 and put it in there, that now matches up with this -1/3 here. So yeah, so the cool thing is, as long as you are careful with your steps each step of the way, and as long as you decide, okay, I'm going to freeze it here and plug in, or I'm going to freeze it here and plug in the values, you just got to know where did you freeze it, and then that's where your C value is going to go back in. If I froze it here, I got -1/3. That's fine. That's where that's going to go back in. There's the -1/3. That's where that will go back in. So the constants change sign depending on how you solve it. Well, because I was being flexible with the C value here. And again, here all we had was a negative going through. But if we had had more implications on that C, maybe we divided it by 4, we did some other things to it, you're allowed to just keep calling it C as long as you, once you stop and you freeze it and you say, okay, now I'm going to plug the values in. Once you get a C value, it needs to go back to that very same line. And again, doing more practice on these problems is a great idea to kind of see. There's sort of a pattern to them in general. You're going to see similar processes over and over again. It's just a matter of getting more and more comfortable with that. Okay, so I believe we had a question about somebody wanted to see one of the movement problems. So I want to take a vote. Problem number 1 was this calculator-friendly escalator problem. We had a rate of change of people. Some people are getting on the escalator, some people are getting off. That's question 1. And question 2 is a particle moving along an x-axis. So it's a little bit more of a abstract wording of a problem. Okay, Daniela wants to see the in and out problem, which would be the escalator problem. The first one, Ali, okay. Okay, well, let's get going on that one then. I'll show you the problem here. And this is a graphing calculator problem. I have to say that for the AP exam this year, because we're all taking it from home and we don't all own our own graphing calculator, that I'm looking for mine right now. that I believe that the problems they're going to give you are not going to require a graphing calculator, but could in fact, you can use one if it's helpful to you, if you happen to have one. But I don't think that they're going to make a problem where it is only possible, because that really wouldn't be fair to the people who don't have their own graphing calculator at home. Nevertheless, this is still a really great problem to look at because of the concept. So we will be using the calculator because we need to on this problem, but that doesn't mean that this isn't going to be super useful for our learning here. Alrighty, so we were given a rate. Here's our rate R, and this is the rate at which people enter the line for an escalator. Okay, must be a really busy building if they have to wait in line to get on that escalator. Maybe it's like BART at rush hour. Alrighty, so this is a rate, and we see that for time 0 to 300, this top rate applies, and then after time is 300, we have a rate of 0. So R of t is measured in people per second. And a nice thing about having a hard copy of this is I can underline or highlight stuff. If I'm having it on my screen, that's fine too. You might want to just jot down a few, when you're taking the real test, you might want to jot down a few of these things that are kind of important. Be really careful as you're copying these down that you're doing them accurately. So T is in seconds, so this is 0 to 300 seconds. As people get on the escalator, they also exit. I mean, let's assume we're going up, okay? So they get on at the bottom of the escalator at this rate. The escalator goes up, and then people get off the escalator at this constant rate of 0.7 people per second. And as we start, we have initial condition of 20 people in line at time 0. And they haven't given us any other names of functions or anything like that. So we might want to make one up. That's often, I like to do that sometimes just to keep track of things for myself. So for instance, on problem 1A, it says how many people enter the line for the escalator during the time interval 0 to 300. So how many people are actually getting into that line? So I'm going to write down a couple things, and I want you to start thinking about, well, how are we going to figure that out? How do we figure out how many people get into that line, right? So I'm going to say, I'm going to call it P of t. You can make up whatever function you want, but for now, let's call this P of t is the number of people in line at time t. Right, so this is the rate that the people are getting into the line, and then this would be the result. This is the actual number of people in that line. And we were given this initial condition that at time 0, there were 20 people. And so we have the rate, and this is our rate in, right? The R of t is our rate in, and 0.7 was our rate out. So this is an in and out type problem. Alrighty, so Daniela says integrate the rate, and Maria says, yeah, what she said. I like that. A great thing to keep in mind, whether it's a position problem, whether it's an in and out type problem, anytime you're given a rate of change, if you integrate that rate of change, you will get a change in amount. So exactly what Daniela said, if we integrate the rate of people getting into the line, we will get the amount or the change in the amount of people in that line. Excellent. So for part A, how many people enter the line? So we don't even want to know, we don't want to figure out how many are actually in the line, because we know we're starting with 20, but we're actually how many are entering the line. So between 0 and 300. So I see integrate. Which rate and through what interval? What do you guys think? There, Maria and Daniela, there you go. You guys are seconding each other's opinion here. So yes, we would want to, since we're looking for the number of people entering the line, entering means we want the rate in, so we're going to integrate the rate in, we're going to integrate R of t, and that is over this whole time interval, 0 to 300, and of course, with respect to time. So then you look at this R of t function, which is 44 t over 100 cubed minus times 1 minus t over 300 to the 7th. Holy moly. And then you go, oh yeah, phew, this is a calculator-friendly problem, because that could, I mean, it's possible to integrate that, but goodness, it looks like we'd need to do some expanding and multiplying out that binomial to the 7th power. And so this is good news that this particular problem is a graphing calculator problem. So in a typical year, when you know you have a graphing calculator problem, you absolutely would want to write down what you did. And then in this case, again, we're just going to use the functionality of the graphing calculator. I have a slightly older one here, but I'm going to go to math and then pick number 9 for integrate. And then I'm going to say 0 to 300. And I'm going to type in this lovely function here, being careful about parentheses and such. So that is to the 3rd power, and then and then times parentheses 1 minus x over 300 to the, oops, not 30. Oh my gosh, that could have been a mess. To the 7th power. Do you guys know about the insert function, by the way? I'm always surprised at how many of my students didn't know that you could go in and, like, if I left that 0 out, I could go back in and hit second insert, and it'll let you, instead of deleting a bunch of stuff, you can just pop a number in there. And then that is, I'm going to say dx. Now notice, this is another graphing calculator thing. Everything here is in terms of t, and my answer and everything should be in terms of t, but graphing calculator, the only option I have when I'm integrating a rectangular function like this is to use x. So I just outsmart the calculator and go, okay, whatever, I know it's a t, but I'm going to use x instead. I've got t or theta. Those are going to show up when you're in theta, for instance, when you're in polar, or t when you are in parametric graphing or integrating, but not anything we need to worry about right now. So I've typed the whole thing in, I hit enter, and I get 270. And I want to make sure that I clearly put, since it's a word problem, 270, excellent. Since it's a word problem, I want to make sure that I answer in words. You really want to be careful with the context of the problem. Well, we got a couple of people got different things. What I would love for you to do is double check what you entered on your calculator. 44 times, I put that x over 100 in parentheses, cubed. And then the other thing I did, and I'm not sure if this is what happened to you or not, but for the 1 minus, for the binomial to the 7th power, notice I put the x over 300 in its own parentheses, and then 1 minus that, close parentheses, to the 7th. Maybe if you got an incorrect number, double check that entry and see if that is what happened. Okay, Akshita got it. Kalia, any luck there? Natalie, you say, okay, cool. I hope that means you got it. Yay, we got it. Was that the issue? Was it a parentheses issue? Yeah, okay, awesome. Yeah, you got to be extra super careful. And like on this one here, I see this fraction, but like, yeah, it's just, I like to just be extra careful and put an extra set of parentheses around a fraction like that. Oh, and you typed in wrong. Yeah, typos will not work out so well for you. So the question was, how many people entered the line? I got 270. So I would write out in words, you know, during the time interval, and I don't want to waste my time with you guys and just writing things out here, but during the time interval, you know, 0 to 300, 270 people entered the line. Sorry, my handwriting got sloppy there. All righty. Then part B says, okay, well, during the time interval 0 to 300, there's always people in line for the escalator. This is a really busy building. How many people are in line at time t equals 300? Okay, so for part B, we want to know basically what's P of 300. So any thoughts on that one? Remember, we do know P of 0, so that might come in handy. How are we going to get the number of people in the line at time 300? Throw out any words you want. And again, this is Yeah, so sorry, pardon me. This, people are saying you use both rates, and in fact, you do have to use both rates because we're saying they are entering the line at this rate, and then they get onto the escalator. So they're actually, it's before they even get on the escalator, they've gotten into the end of the line, they're waiting in line, and then as they get onto the escalator, they're exiting the line, and that's at that exit rate of 0.7. So yes, we're going to find the antiderivative. Correct, Kalia. You are going to use both rates. Yes, Daniela. And Natalie says the initial condition plus the integral. Yes, you guys have got this. So some finer details here. I know that number of people at time 300 is going to be that initial condition, so P of 0, plus the change in the number of people from time 0 to time 300. So we are going to integrate from 0 to 300. The change in the number of people. There's two ways you can express this. You can say, I'm going to integrate R of t, that's the people coming in, and then I'm subtracting from that the integral from 0 to 300 of my out rate, which was 0.7 dt. Or you can actually combine those together as one, combine an in and out rate. This is the in rate, this is the out rate. You could have an in and out rate and just have that be a single integral. Excellent. Natalie, you're ahead of us and you're doing great. Good job. So P of 0, of course, is 20. And then we're going to integrate from 0 to 300. The exact same thing we typed in before, that 44 t, of course, on the calculator will say x over 100 cubed, 1 minus the t over 300, close parentheses, to the 7th. And then I'm going to subtract 0.7, and that is all dt. So you'll notice I wrote the in and out together as one rate. Good job, folks. Very good job. And you are correct that that should give you 80. That is the right answer. Could you integrate by putting both rates in? Absolutely. And that's what I just did here. You'll notice there's one integral sign here, and I combined them both. You also could do two separate integrals. But again, I like the path of least resistance. And when you're using the graphing calculator, why not, as long as you can carefully type things in and keep it straight, there you go. I am going to move on to part C. And again, you want to put this answer in a, in words. So I would say, let's see, during the time, there's always people in line. How many people are in line at time t equals 300? At time 300 seconds, there are 80 people in line. Yes, don't forget the initial condition. In fact, I wrote it again here, and I had underlined it because that's something we want to remind ourselves about. Alrighty, part C says for time greater than 300, what's the first time that there's no people in line for the escalator? So I'm going to move this aside, get a fresh page. For time greater than 300, when's the first time there's no people in line? And what you'll notice is at, there you go, for t greater than 300, our rate in now is 0, okay? So what we know for part C is that the number of people at time 300 is 80, because we just figured that out in part B, and we're actually now going to use that in part C. This is like a new initial condition. And then we want to figure out, let's see. So now for time 300 on, nobody's getting in line. We just have people getting out of the line, right? Nobody's coming to the end of the line. They're just keep getting onto the escalator. So the people in the front of the line keep getting out of, going on and on. So our line gets shorter and shorter. So we're trying to figure out at what time does that equal 0? This one's a little bit trickier. Any ideas how to set this up? It's very similar to part B in some sense. Natalie, I'm not sure, Natalie, where the 300 comes from. I think, I know at time 300, the number of people is 80. So we're actually looking for, oh, I see what you're saying, time 300, okay. I'm not sure, let me double check whether that works. I did it a much more complicated way. You said 300. Holy moly, you got it right. The way I did it is way harder. Hang on a second. Lovely. I got really calculus-y on this one. Natalie, what was what Natalie said is, okay, I had, there was time 300 plus, and you got, Natalie's going to get a 5 easy. Yeah, I hope so. Good job. Then you added 80 divided by the rate, because this is 80 people that are in line, and you were dividing by this rate, which is people per second. And that kind of makes sense, because if I kind of think about, people divided by people per second, kind of think of multiplying by the reciprocal of a fraction there. So 300 and plus the 80 over 7, 80 over 0.7 was 114.286 if we round off to 3 places. And of course, people divided by people per second means I'm multiplying by seconds over people. And that gives you how many seconds it takes for those 80 people to go away. Beautiful. Simple, elegant. I do hope you get a 5. That was well thought out. The way I did it is a little bit more complicated. I think, honestly, it's not worth even complicating it for you guys. I think that is elegant and lovely. And the idea of, well, you had 80 people in line and we had to remove them. We know the rate of removal. There you go. Beautiful. Part D, this part actually does use the calculator again. Oh, Akshita says, can I walk you through the procedure? Yes. And I think we're running low on time here, so I will do that, and then we'll do part D, and I think then we have to call it a day. So I have it actually pre-written, so I'm gonna show you my process here, which is I made up an equation. I said there's some time X. I don't know what the time is. That's what we're trying to figure out. But there's sometime X where X is greater than 300. And I know there's 80 people in line. And then I want to say, well, at this time after 300, and I can even say plus, because this is like there's 0.7 people leaving the line every second. So I'm going to integrate from 300 to whatever that unknown time is. So number of people at that unknown time is the number of people at time 300 plus the integral from 300 to that unknown time of the rate at which people are exiting. And when you do that, you're going to get, we're integrating, oopsie, that should have a t there. So you integrate negative 0.7 with respect to time, and you get minus 0.7t, and I'm integrating that from 300 to x. So I have 80 minus, and of course then I evaluate from top to bottom, so 0.7 times x minus 0.7 times 300. See how this is way more complicated than what Natalie came up with. And simplify, 0.7 times 300. I end up with 290 minus 0.7x, and I'm trying to figure out when there's no people left, so I set that equal to 0 and solve for x. Way, way more complicated than what our friend Natalie came up with, so good job. Part D, last but not least on this problem. Part D says, for time 0 to 300, we want to know when the number of people in line are at a minimum. And to the nearest whole number, we're going to find the number of people in line at that time. So we want to know, yes, Ashita, the P of X was my function I made up earlier on the problem. That's how many people are in line. So yes, P of X would be the number of people in line at this unknown time, sometime past 300. And I started at, so this is P of 300 here, plus that change from 300 to time X. Okay. So, and really, back to your question, Akshita, and some other previous problems we were doing, basically there's sort of the idea of the accumulation problem is really good to keep in mind. If you have, some f of b that you're looking for, and you know there's some f of a, let's say where a is some time value less than b or some x value less than b, then I can start at time A and then add that integral from A to B. Right, so this is saying how much of whatever this function is do I have at time F? Well, let's start at my initial condition at time A and integrate from A to B to get this, right? And maybe I'm looking for, maybe this is the unknown one, in which case then I could say, well, f of A is equal to f of B minus that integral from A to B, f prime of x dx. Okay, so that's the basic concept that I was using there on that prior problem. Again, made it more complicated than I needed to, but there you go. So problem D, similar idea. I want to figure out where my number of people line is a minimum. And we're going to need to use the graphing calculator for this. Let me see if I have it already plugged in. I do not. So in order to come up with a minimum, I need to figure out basically what's happening with that rate in and out. So I'm going to go ahead and graph the rate in minus the rate out. So 44x over 100 quantity cubed times 1 minus parentheses x over 300 close parentheses to the 7th minus 0.7. Feel free to graph that with me. And I'm going to set the window. I need my x values to go up to 300. And I think the y values can be pretty small here. So let's take a look at what happens. Yeah, I kept my y values between negative and positive 3. This problem is a nice one because this is a rate, right? This is the rate function. Basically the rate in minus the rate out. So this is the overall rate of change of number of people in the line. And we want to know at what time is the number of people in line at a minimum. Now they don't say absolute minimum, but I think that's what they are implying there. Like what time do we have the least number of people? That's our absolute minimum. So a thing to keep in mind on an absolute min or absolute max problem is not only do we need to look at critical points, we also need to look at endpoints. And so luckily we already know the number of people in line at time 0, which was 20. And we knew at time 300, we solved and figured out that that was 80. So let's look at our graph and see if there's any useful information here. What I see is, okay, again, at time 0, I had 20 people in line. Because my rate graph is below the x-axis, that means I have a negative rate of change, which means that the number of people overall are decreasing. So I'm going from 20 people and I'm losing people from the line until we get to this point here on the graph, where now my rate of change goes positive. So this would be considered a relative minimum, right? This, where the slope is 0, or excuse me, where the rate of change equals 0 on the graph here, because my rate goes from negative to positive. And if I think about that, a negative to positive slope, that's going to give me at that changeover a relative minimum, negative to positive, relative min here. Then I have positive slope. So now the number of people in line are increasing until I get over here. And now I have a relative max because I know my rate of change goes from positive to negative. We max out positive to negative. And then I see negative again, so I have decreasing. However, I know it only decreases as far as 80 people. So already when I'm looking for an absolute minimum number of people, I can already rule out 80 because 20 is less than 80. So what do you know? And so then really what I need to figure out is what time do I have right here at that relative min and how many people are in line at that time. So you do want to use your graphing calculator, or maybe you have Desmos up, either way. You want to figure out that time. Natalie, you're already a step ahead of me again. I love it. So I'm going to go to the calc here. So second and then calc. And I want to find that 0. So I'm going to pick number 2 for 0. And then it asks me for a left and a right bound. So I'm going to slide this cursor over. Come on, slide, slide, slide. Go. So that we are just to the left of that intersection point. Hit enter. Just to the right of that intersection point, hit enter. And of course, it might be smarter for me to have maybe zoomed in a little closer on this, but I think we're going to get decent results anyway. And then they want to guess, so I'm going to get pretty darn close and hit enter. And it gives me the X value of 33.013. Natalie, Maria, we all agree with each other. So we're looking at time equals 33.013. And then the question is the number of people in line at that point less than 20? If it's less than 20, then that's our minimum number of people. Otherwise, 20 would be our minimum. Well, once again, to figure out how many people are in line at time 33.013, we have to use that accumulation idea, taking P of 0 and then adding, just like we did before, our rate of change of people. And you can, once again, you can do it as 2 integrals or 1. I'm going to do it as 1. I'm going to combine my R of T, my rate in, and I'm going to subtract my 0.7, which is my rate out. You pop that into your calculator, and that will give you the number of people. So let's do that real quick. So I've got, I'll quit here. I'm going to go to math and then 9 again, and I'll just do the integral. Then we'll make sure to remember to add those 20 people in a moment. So I'm going to integrate from 0 to 33.013. Excellent. And once again, 44 times X over 100 quantity cubed times 1 minus parentheses X over 300, close, close, to the 7th, and then minus our 0.7. That is with respect to X. And what I get here is the change in number of people, right? This integral of a rate gives me the change in the number, the change in the amount. So I had 20, and I get minus 16.19656, say. So basically, I'm going to take that value in my calculator, add 20 to it, and that tells me that I have approximately 3.803 people in line at time 33.013. And it did say to the nearest whole number. So I'm going to round that up. I'm going to show this because I want to make sure I'm showing all of my evidence clearly. So this is the answer. But when I answer in words, I will say at time 33.013 seconds, we had the minimum number of people in line, which was 4 people. Now, clearly, you could probably write that more elegantly than I just did, but you want to basically include clearly what they're asking for, specifically when, all that jazz. Okay. Any final questions before we wrap up our time together? There were some questions. People asked, what are the best ways to practice for the exam? I think one of the best things you can do is to find old free response questions like these. And one of the best things you can do is practice the time anxiety. Give yourself 15 minutes, put a timer on and go and just do your best and see how it turns out. You can always Google the or find the answer rubrics on the College Board site. You should be able to just pull them up on Google, no problem. Put in the year. These were the 2018 the 2018 exam problems that we were looking at today. We only got to 2 of them, but there's 4 more, and the answer keys are available online. Next week, next Monday, we'll be looking at the 2019 problems. Daniela wants to know, will the AP exam test slope fields? It's in the realm of possibility, Daniela. I think they're going to try and get a nice broad swath of problems, but I would be shocked if you didn't see some accumulation problem or in and out problem like we were talking about today. I just have this hunch that they're probably going to do something related to the separable differential equations and maybe tracing through a slope field. But again, the logistics on that, if people don't have printers, does make it a little tougher. but they were doing a whole series of lessons on those on the College Board website through YouTube. So those are all available if you haven't seen them yet. So you are so welcome. I look forward to seeing some of you guys next week, same time. We'll look at 2019 problems. Feel free to Google those problems in advance and take a look at them and see if you have any specific ones, because clearly we won't get to all of them, but if you have specific ones that you'd like to look at, take a look at it in advance and let me know. Natalie, is there a stream like this for the BC FRQs? Officially, no, but I teach BC as well. So if there's a 2019, why don't you go ahead and take a look at the 2019 BC problems. A lot of the BC FRQs usually include 4 AB problems. So these are right in your wheelhouse, plus like 2 that have BC specific. That's in a typical year. This year, since it's a little, things are different, they probably will have at least part of a problem BC specific. So once you peel through the 2019 problem, see if there's anything specific you want to talk about. And I'm happy to take that request next Monday when we're looking at the problems together. Thank you so much. This is my first one. I hope it made sense. I hope it went well. I appreciate your guys' cooperation and participation. Thank you.